The life cycles of stars are some of the most intriguing processes in the universe. At the end of certain stars' lives, they undergo a violent and spectacular event known as a supernova. This explosive event not only marks the dramatic conclusion of a star's existence but also leads to the formation of stellar remnants, dense objects that remain after the explosion. Supernovae and their resulting remnants provide scientists with valuable insights into the fundamental workings of the universe, including the creation of elements and the fate of massive stars. A supernova is a powerful explosion that occurs at the end of a star's life cycle. It represents one of the most energetic events in the universe, briefly outshining an entire galaxy and releasing enormous amounts of energy into space. Supernovae can be classified into two main types. Type 1 supernovae. These occur in binary star systems, where a white dwarf star accumulates matter from a companion star until it reaches a critical mass. At this point, it can no longer support its own gravity and undergoes a catastrophic collapse, leading to an explosion. Type 2 supernovae. These are the result of the collapse of the core of a massive star that has exhausted its nuclear fuel. As the star's core contracts under gravity, it heats up and eventually triggers an explosion. In both types of supernovae, the energy released is so immense that it can briefly outshine an entire galaxy. The explosion also causes the star's outer layers to be ejected into space at high velocities, dispersing elements such as oxygen, carbon, and iron into the surrounding interstellar medium. Supernovae play a crucial role in the cosmic cycle. The elements produced in the core of stars during their lifetime are mostly confined to the star itself. However, during a supernova explosion, these elements are released into space, enriching the interstellar medium with heavier elements that can later be incorporated into the formation of new stars, planets, and even life itself. Without supernovae, many of the heavier elements found on Earth and in other planets would not exist. Moreover, supernovae contribute to the dynamics of galaxies. The shockwaves from the explosion can trigger the formation of new stars, influence the movement of gas and dust, and even affect the evolution of the host galaxy. Supernovae are, therefore, not only explosive events but also key drivers of cosmic evolution. After a supernova, the remnants of the star depend on its original mass. Stellar remnants are the dense objects that remain after the outer layers of the star have been expelled. These remnants can take several forms. Neutron stars. If the star's mass is between about 1.4 and 3 times the mass of the Sun, the core that remains after the supernova will collapse into a neutron star. Neutron stars are incredibly dense, so much so that a single teaspoon of neutron star material would weigh about 1 billion tons. These stars are primarily composed of neutrons and exhibit extreme magnetic fields and rapid rotation rates. Some neutron stars, known as pulsars, emit beams of electromagnetic radiation that sweep across space like a lighthouse. Black holes. If the original star is massive enough, its core will collapse into a black hole. Black holes are regions in space where gravity is so strong that nothing, not even light, can escape from them. The formation of black holes is one of the most fascinating aspects of stellar evolution, as these objects challenge our understanding of space, time, and gravity. Once a black hole forms, it continues to accumulate mass by attracting nearby material, often generating powerful jets of particles in the process. The study of supernovae and stellar remnants provides essential information about the fundamental processes governing the universe. By observing supernovae, astronomers can learn about the chemical composition of distant stars and galaxies, the rate of star formation, and the history of stellar evolution. Additionally, the study of neutron stars and black holes helps scientists understand the behavior of matter under extreme conditions, contributing to our understanding of general relativity, quantum mechanics, and the nature of spacetime. Supernovae also act as cosmic distance markers due to the predictable nature of their brightness. Type Ia supernovae, in particular, have been used to measure vast cosmic distances and have led to the discovery of dark energy, a mysterious force that is driving the accelerated expansion of the universe. Supernovae and their resulting stellar remnants are among the most profound phenomena in astrophysics. They represent both the violent end of a star's life and the birth of new cosmic material that will go on to shape the universe. Whether through the formation of neutron stars and black holes or the dispersal of heavy elements into space, Supernovae play a vital role in the ongoing evolution of the cosmos. By studying these events, scientists continue to unlock the mysteries of the universe.